So hello to all. I believe you can hear me. So we are ready to start the session that has the electron view. First, we have a presentation from our technical manager, it's Panagiotis Radoglou, that will provide an overview of the electron, the 4 pillars of electron, and the use cases. So let me share the screen. Just a minute. Sound από τώρα. Όχι, τώρα δεν χρειάζεται. Βίντεο δεν έχει sound.
Έχει sound στο βίντεο τώρα.
Τώρα. Okay, so.
Θα το μέσα από πάνω. Δεν το καταλαβαίνεις.
Δεν καταλαβαίνω που είναι.
Okay. Hello everyone. This presentation is an overview of the ELECTRON project. First of all, ELECTRON is a DS4 project, an innovation action, coordinated by net company Intrasoft, while the University of West Macedonia is the technical manager of the project. The overall budget is approximately 10 million. And in general, the goal of the project is to provide cybersecurity and safety services, especially designed for the energy domains. The consortium of ELECTRON is composed of 35 partners, combining both industries, SMEs, research centers, universities, in order to create a collaboration model that can handle various security scenarios that will be discussed later. So regarding the business logic behind ELECTRON, this is composed of 4 main frameworks: the border framework, the cyber framework, the bridge one, and Prince. Border is responsible for the collaborative risk assessment and the cybersecurity certification. On the other hand, cyber integrates a wide range of intrusion detection, correlation, and threat intelligence services. And based on these security events, then Bridge integrates mitigation and remediation related services based on 2 main axes. The first pillar is to leverage IT solutions for mitigating potential intrusions, and the second pillar is to adopt energy-related countermeasures in order to avoid potential large-scale disastrous consequences. Finally, Prince is related to cybersecurity awareness with respect to the readiness of the energy personnel by leveraging, let's say, AR and VR technologies. So, some more details regarding each framework. First of all, border is composed of 3 main components: the Army component, Darcy, and the Hane Potasa service. The Army component is responsible for the collaborative and dynamic risk assessment by integrating, let's say, asset identification, threat identification, vulnerability identification, and the calculation of the risk values based on the live security events that are detected by the cyber framework. Next, Darcy is focused on cybersecurity certification with respect to the energy assets, and also the role of Darcy within the integration model of ELECTRON is to provide, to indicate, let's say, potential mitigation actions. And finally, Honeypot as a service is a countermeasure in order to enhance the security of the energy infrastructures by providing honeypots dynamically and following the cloud model. On the other hand, the Cyber framework is composed of more components compared to Border, the ELECTRON CM, FLIDPS, APT Strongbox, ELECTRON Threat Explorer, and the ELECTRON SharePoint. First of all, FLIDPS and APT Shield, Strongbox, and also other detectors like LADS are organized through a CM system called ELECTRON CM, and these detectors send these security events to the ELECTRON CM, which is responsible for normalizing their format and correlating these security events with each other in order to compose security alerts. It is worth noting that also Strongbox is mainly an anomaly-based detection system, which adopts private-aware AI services in order to detect potential anomalies. This means that Strongbox combines, let's say, both artificial intelligence and cryptography techniques in order to apply anomaly detection based on encrypted data. Finally, the ELECTRON Threat Explorer is a data mining mechanism in order to identify and explore potential threats, new threats related to the energy sector. And the ELECTRON SharePoint acts as a decentralized repository where the energy organizations can share, can exchange their security events in real time. Next, based on the security events, on the security alerts generated by Cyber, breach includes the mitigation and remediation services, and actually it consists of four main components. The ISODIN component, ELISE, NERO, and BIM. First, ISODIN is responsible for intentional proactive islanding in order to avoid, let's say, large-scale catastrophic events with respect to the nature of the energy domain. Then, based on the islands created and indicated by ISODIN, ELISE is responsible for the grid restoration. And on the other hand, NERO can take into consideration the potential mitigation actions provided by the DARSA component and selects the most appropriate one, considering, let's say, potential costs and rewards. And finally, BIM represents a blockchain-based decentralized energy information sharing center, allowing, let's say, the organizations to share with each other security events. Finally, Prince represents, let's say, a AR, VR cybersecurity training platform, including multiple scenarios such as false data injection, unauthorized access scenario, spear phishing scenario, and also physical threats. Now, all these solutions implemented by ELECTRON are evaluated and validated during this time frame in the context of 4 use cases. The first use case is carried out in Ukraine, and one scenario will take place in Azerbaijan. Here we have actually 5 scenarios. The first scenario is related to spear phishing, showing how the Prince framework can train and educate the energy personnel in order to avoid spear phishing attempts. The second scenario is related to countering relevant energy-related malware by detecting, let's say, their presence. Then the third scenario focuses on detecting and mitigating SCADA-related attacks by paying special attention to activities that can violate energy-related protocols like EC 104. And actually, scenario 4 is another unauthorized access attempt related to other protocols, to other energy-related protocols like Modbus, while the last scenario of this use case is focused on detecting and mitigating the denial of service and distributed denial of service attacks. In all of these scenarios, as I said earlier, special attention is given to counter not only, let's say, TCP/IP attacks, but also application layer attacks. Now, the second use case focuses on the electrical vehicles infrastructure. Here we have 4 scenarios. The first scenario is to identify any assets that are not, let's say, sufficiently secure, and we need to isolate them. Next, the second scenario is focused on countering, on detecting and mitigating false data injection attacks against electrical vehicles charging stations. Similarly, scenario number 3, is related to denial of service attacks against EV charging stations. And scenario number 4 emphasizes the importance of detecting man-in-the-middle attacks. For all of these scenarios, I need to say that the same collaboration model between the ELECTRON components is used in order to detect, identify, and mitigate the attacks. Then, scenario use case 3 is carried out in Spain, and here the goal is, actually this use case includes 3 scenarios. The first scenario is related to train again the energy personnel regarding potential cyber attacks and malicious activities. Again, Prince is used for this purpose. And the second and third scenarios focuses on unauthorized access and denial of service attacks, where, let's say, a workflow of the ELECTRON components, including detection, real-time correlation, real-time risk calculation, and attack mitigation take place. And the last use case of ELECTRON is conducted in Romania, including the DSO, and DSO of Romania. And here, this use case includes 5 scenarios. The first scenario is related to countering false data injection attacks against TSOs and DSOs. Then, in a similar manner, the second scenario focuses on unauthorized attacks, coordinated unauthorized attacks against the Transelectrica and Electrica that are the TSO and DSO of Romania. Similarly, the third scenario is related to distributed denial of service attacks. By combining all these attacks, next in scenario number 4, we are focusing on countering, on addressing coordinated advanced persistent threats as a set of multi-step attack scenarios, while scenario number 5 assumes that the cyber attack is already ongoing and we need to achieve, to accomplish, let's say, real-time islanding in order to protect the overall grid of Romania. And in this scenario, islanding schemes and restoration activities by Isodin and Elise are emulated. So this was an overview of the ELECTRON project. I don't know if there are any questions, any comments.
Okay.
Okay, can we go ahead
Thanks.
to demo?
Yes, let's. How much? Sure.
Το βίντεο θα δείξω. Έτσι το εξηγεί. Άνοιξε την παρουσίαση, την άλλη, είναι σε τέτοιο. Και λογικά πρέπει να υπάρχει ένα link στο τέλος.
Το είδα.
Δεν υπάρχει το link. Δεν ξέρω αν υπάρχει. Εγώ είναι στο ELECTRON τότε. Εγώ είναι στο SharePoint. Βλέπω το Pro.
Πρέπει να πάω να κλείσουμε το Χρήστο.
Ναι, ξεκινήσουμε.
So, thanks again, Panagiotis. So, we have a slightly change in the agenda. So, we will do the presentation of the CTI framework of ELECTRON, the CTI platform of ELECTRON. So, I will give the floor to Christo Kostousanki from Matos to do the presentation. Christo, you can hear us, I believe. So, just a minute to minimize the window so we can see your screen. So you can proceed. Christo, you are muted.
Okay, now you can hear me.
Yes, loud and clear.
Yes, sorry for that. Okay, sorry for this slight change. From our side, we also we have some overlapping activities today, so we would prefer to present you now the ELECTRON CTI platform. It's a collaborative work between Eviden, which is part of Atos Group, it's a company, and Idenner, it's an SME in Spain. So that's about the talk is about the presentation about the ELECTRON CTI platform. It's a cyber threat intelligence platform that allows and the objective is to facilitate stakeholders in the electric power and energy systems domain to share vulnerabilities, threat information, URLs, suspicious URLs, IP address, etc. So that's the main objective, to allow such sharing of CTI data. Of course, there are two main aspects as well. One is to facilitate anonymization and security capabilities of such sharing. So once you share data, you would like to enforce some security on this data, like anonymization of some fields or encryption of other fields, which you would like to be able to control confidentiality on such data when shared with others, so others they can selectively see only that part which you have decided to hide, to confidentially store for them. So there are two main components of the CTI platform. One is actually the CTI SharePoint, we call it. It's the platform that allows to share actual data and to use security features on that. And also we have a Threat Explorer component, which allows to discover threats and vulnerabilities from open source intelligent repositories. So these are two main components. Let's first look at the CTI platform, the SharePoint, CTI SharePoint, we call it in the project. So we have a backend and the front end. So the backend is one or more MISP objects, MISP nodes operating. So MISP, it's a well-known platform for sharing threat intelligence, malware information as well on its origin, but it's a well-known in open source community platform. So there are nodes, servers, MISP servers behind. So we have, that's the backend. In the project, we have one main, which allows to interconnect with other external stakeholders in the community. And we have a front end to such backend, which allows to enforce certain security aspects on the data, as well as to share data securely or selectively with other stakeholders. So the front end is actually a nice addition to the backend, which is the MISP technology already used in the community. So as I said, this front end is confidentiality management, in which you can share data only when you're confident and you want to enforce that confidentiality. So we want to be confident that the data is not read by anybody, but only by the selective stakeholders you would like to share, or you want to completely anonymize or erase some fields when you share such data with the external world, with other stakeholders you would like to collaborate with. And we have scoring. CTI scoring is also very relevant aspects, an aspect which allows you to automatically identify the relevance of vulnerability, for instance, when received from the external world, from the external stakeholders with your infrastructure. So this also automates and allows a high level of automation in which what vulnerability CTI objects applicable to your infrastructure as a pilot or as a stakeholder which operates EPS system. Okay, so that's about the CTI SharePoint. About the ELECTRON Threat Explorer, it's an additional component which it's a service that can be run on a machine that doesn't need to be on where the MISP for the front end is stored. Could be an external machine which allows to on a daily basis to retrieve CTI data from the open source intelligent resources. So what we did here, we did a specialized service, which is only for the power grid SCADA protocols, IEC 104, DNP3, Modbus, IEC 61850. They have there's a family of protocols there. So for all such relevant to our project and pilots in setups, test beds, in devices and manufacturers. So we've covered this domain well. So it's very specialized CTI data retrieval, but it's actually a very useful one. So looking at the CTI architecture, it's a scheduler and a set of crawlers. So we can crawl open source intelligent resources on a scheduled basis, and you can retrieve vulnerabilities, not that information based on keywords expressions. So you can have expressions of keywords, and you can then automatically retrieve those and filter those set of vulnerabilities on daily basis and store them in the ELECTRON CTI SharePoint that we have just mentioned. So as a result of this, we have designed the Threat Explorer to cover all data since 2020, when the pandemic began, and also when we had to explosion of different vulnerabilities and the cyber attacks that have increased exponentially. So since 2020, we have actually covered surprisingly more than 600 vulnerabilities, which are specialized and relevant for the industrial control protocols in the power grid domain, but as well as for the different devices that is used in the project, in the test beds. So this is the result, interesting. So it's a number of vulnerabilities which are relevant for the domain of ELECTRON. So these are examples you can see of such keywords, but there are more which we've come up, which allowed us to actually have such a database of vulnerabilities available for the project. And also we're looking forward for collaborations, and if someone is interested to further expand this on their own field or projects, etc. Of course, open source intelligence, there are many databases and sources of reference where we've been designing and performing these Data Explorer evaluations, we've come up only with a subset of such resources, which we found as first to publish a relevant vulnerability to our domain. So there are many more, but we've selected only those which are first publishing relevant vulnerabilities, though the rest they are duplicating or not of relevance to us. So this is the list which we curated, and we are also maintaining this list up to date by now. Okay, so that's about Data Explorer. About the Electron CTI SharePoint, my colleague Esteban will give you a bit more insight about this, and will show you a demo, a video of the demo.
Okay,
Please.
can you hear me? Can you hear me?
Suppose yes, yes,
All right,
yes.
thank you then. All right, thank you, Risto. All right, so carry on with the explanation of what is Electron SharePoint. Oh, great. So as already explained, Risto, mainly the SharePoint has two main functionality. Let's say the one that is the enrichment of the IOCs, the enrichment of the events coming through the different sources into the instance that we have deployed in the project, and then the sharing capabilities. Okay, so for the event enrichment or the IOC enrichment, firstly, we calculate the score, as already mentioned, Risto. We calculate the score based on different features that we extract from the different types of events that came into our MIST instance. Right now, we are focusing on vulnerabilities, but it can be extended also to different other IOC types or IOC attributes as well. Then, after we calculate that score, which is particularly focused on the topology base of the client, we map that vulnerability to the assets that can be affected by this particular vulnerability or IOC that we found. Okay, then the second part of the SharePoint, the Electron SharePoint component, basically is sharing those events with the relevant stakeholders. Okay, so by using MIST, we have the transport layer covered, let's say. Nevertheless, the idea of this Electron SharePoint is giving this extra layer of security to those particular events that we want to protect by using keep using the public, let's say, the public channel of this communication among the MIST instances connected in the network. Okay, so by doing that, we can anonymize the information within the events. We can encrypt the information, and that can be only read by the specific person or a specific role or a specific organization that we want to read, and for a specific time period. Okay, that is why also was mentioned by Risto, the front end of the Electron SharePoint. Okay, so next slide, please. All right. So as I was saying, the CTI scoring or the scoring of the events is being carried out by extracting 4 different attributes. In this case, we extract the relevance, the trending, the timeliness, and the completeness. Each of these features give a particular weight into the final value of that score. So based on that particular attributes, we can also tailor the different scores that we want to have for particular IOCs or particular events for our own infrastructure. And in that way, we can have an ad hoc score instead of having a generalized information or scoring for our infrastructure particularly. Now, based on what we already explained, I would like to share with you a small video demo of the capabilities that we already discussed. It's a video of 2 minutes. Okay, and so I will take the screen sharing. So just a second. Okay, I hope that you can see my screen. Can you see my screen?
Yes, yes, we
Yes.
All right, great. So there you go. It's okay?
It's
Yes,
sound.
perfect. We can hear the sound. It's okay.
It's okay because I hear like it's
Distort. No, if they hear well, go
yeah,
ahead.
distortion, right?
Can you play it
Let
again?
me
Play again. Play again.
Yeah, yeah. So sorry for about that. Let me do it again. I'm sorry for that delay. Okay, just a minute.
Hello and welcome to the demonstration of the ELECTRON SharePoint component. The ELECTRON SharePoint, or ESP, is comprised of various components and services. At its core, ESP employs a MISP instance for transport and communication mechanisms. The ESP's key features are the Threat Intelligence Engine, TI, component responsible for calculating the risk score of vulnerabilities, and the Secure Sharing component, which provides the ability to encrypt and anonymize information to share securely. ESP offers a web application and an API for interaction and integration with external services. In the following demonstration, we will explore the functionalities of these components in detail. Accessing ESP's MISP instance, we see events from the ELECTRON Threat Explorer, each tagged with a TI taxonomy indicating its auto-calculated risk score. Drilling down into an event, two new attributes appear: the score and the affected asset's UUIDs, fed from Tindit's network topology data via the SDN component. For this demo, we'll use an unpublished event, pushing it to the 0MQ queue. Once queued, TI processes it, calculating the score, visible on the live logs on the terminal's left. Immediately after the event is published in the queue, it is picked up by the TI component and its score is calculated. We can observe this in the logs that are shown in the terminal on the left side of the screen. Refreshing MISP, the event now shows the TI tag and new attributes, including the score and affected assets. Next, we'll demonstrate secure event sharing on the ESP web app, with Alice sharing an event with Bob. The ESP, configured for MISP communication, presents a form under the Share tab. We input the event for Bob, encrypt the description, add tags, specify Bob as the receiver, configure attribute sharing options, encryption, anonymization, or plain text, and set an expiration date. Hitting Share completes the process. In the ESP's MISP instance, a new, encrypted event appears. Switching to Bob in ESP, a new, readable event is on the dashboard. Inside ESP, the once encrypted attributes are now decrypted and readable. This demo highlights ESP's secure, efficient data sharing capabilities, emphasizing encryption, controlled access, and seamless user experience.
Okay.
I hope that that is clear for you. So I'm open to any questions that you may have.
So thank you, Christoph. Thank you, Esteban. I don't know if we have any questions from the audience here in Hamar. No, any questions from the online audience? No. So once more, thanks again for your
Thank you.
presentation and
Thank you very much.
support. So,
All right. Thank you then.
bye.
Thank you. Bye.
So now we have a demo presentation from Panayotis. Let me try to see if that works. Give me a minute. So it's this one. Oh. Let me see if it works. What here? Let's see if we can have the feed the audio. Otherwise,
Choose the screen. The left, not this one.
Don't know what you say. It's about the.
The previous. Go back.
Yes.
Yes, the screen. Yeah, how to call screen.
This one, it's this one to share the sound, but it doesn't work.
Not the other one. Here, it's here. Left, to the left, yeah.
This one?
No, under it. Under it.
This? I don't know what it is. For the sound is this one.
Yes. If you can share the screen, not the application.
Full screen, yeah.
A full screen.
I think I'm saying this. I don't know what this one. This one. It hasn't anything about that. Then I don't have the option now to do it.
If you now share you can see the video.
The video I can see, but for the sound I don't know.
Have you included the sound?
No, it doesn't work. So sorry for that, but the online audience cannot hear the sound. Sorry, but the online audience cannot hear the sound. I will try to share it through my PC and see if that works.
For this demo, the experimental testbed of PPC will be used. This testbed is also used in the context of use case 2. In this demo, the attacker targets the charging station management system through OCPP attacks. The attacker uses session establishment denial of service attacks that attempt to establish a WebSocket session with the charging station management system. Although the charging station management system is appropriately configured to reject connection attempts from unknown electric vehicle charging stations, the attack can significantly impact the charging station management system's performance. Before showing the various steps of this demo, let's see first the status of PPC SDN experimental testbed through the ELECTRON SDN controller and dashboard. This is the login page of the SDN controller and dashboard. This is the home page of the dashboard, where we can see all connected SDN switches. For this demo we use one Aruba 2930F SDN switch. By clicking on In, we can see a summary of the switch ports with various information and statistics. Moreover, we also see the connected SDN controllers and the role of each one. The first SDN controller is identified as master. Next, we can see the topology map, which plots all hosts discovered by the SDN controllers. Particular hosts can be inspected in the asset inventory. We now select the host that is targeted by the attacker in this demo. For this host, which is a charging station management platform, we can see various information, like the MUD URL, network details, and running services. Finally, in this page, we can see the flows installed on the SDN switch. Table 0 is the entry point and table 100 contains all the flows inserted by ELECTRON. Now we sort the flows based on priority, so the flows with greater priority are parsed first. Currently, no security rules have been inserted by ELECTRON. Regarding the workflow of this demo, while the attacks are executed, the first steps are the detection and correlation of the security events from FLIDPS and the ELECTRON SIEM. First, FLIDPS is responsible for capturing the network traffic data, generating OCPP flow statistics and detecting the attacks. Next, the security events are transmitted to the ELECTRON SIEM through re-syslog. Then, ELECTRON SIEM is receiving the security events from FLCM and normalizes them. Through the dashboard of the ELECTRON SIEM, specific details about the normalized events are available to the end user. Next, the ELECTRON SIEM associates the security events with each other, thus composing security alerts. For this purpose, specific security rules are used. Finally, based on the dashboard of the ELECTRON SIEM, various information is also available to the end user.
Now we proceed with the presentation of ARMY component, which is responsible for the initial, but most importantly, the dynamic risk assessment of the topology. ARMY is based on the holistic project realized by Ubitech. In this part, we are about to see how a new security alarm raised by the ELECTRON SIEM component triggers a new risk assessment which is executed on the entire asset topology. On the right-hand side of the screen, we see the dashboard of ARMY, while on the left-hand side we see the logs of the ARMY's connector to the events reported by ELECTRON SIEM. Upon arrival of a new alarm from ELECTRON SIEM, we observe that a new notification is issued in ARMY on a specific SDN host asset. This immediately triggers a new risk assessment task being executed in ARMY. The calculated risk assessment results per asset are published through Kafka to Darcy. The results contain asset information such as the device ID, the computed individual risk level, the associated threats and vulnerabilities, the alarms raised, and the controls that have been applied so far. All this information is used by Darcy to associate mitigation controls with assets. As we see in these terminals, Darcy internally launches two services that calculate the possible mitigation actions to be enforced, depending on either the MUD device identifier or the MUD threat identifier. Both services are displayed on the top left and top right terminals respectively. The computed mitigation controls are expressed in MSPL and published back to ARMY through a new Kafka message. In the Kafka consumer of ARMY, we observe the receival of the MSPL messages from Darcy, which triggers the creation of new notifications that record the addition of new mitigation control entries in ARMY. The addition of the new controls is also depicted in the relevant controls tab. Based on Darcy's response, 3 controls are associated to specific device IDs and 4 controls are related to specific vulnerability identifiers. By inspecting a control entry, the user notices the MSPL information provided by Darcy. The controls proposed by Darcy are now available to Nero through ARMY.
The next steps of this demo are to choose the appropriate mitigation action and guide the ELECTRON SDN controller to stop the attack in real time. This is done by Nero and the ELECTRON SDN controller. Nero receives the risk information from ARMY and Darcy, including a set of potential mitigation actions and selects the appropriate one. Then, Nero uses the API of the SDN controller in order to execute the mitigation action. Finally, the flow tables are updated by the ELECTRON SDN controller, thus stopping the attacks.
So I believe you can see the presentation. I don't know if someone has any questions. Okay, so we can continue with the next presentation. It's done by Alon Adil from IBM. It's about the anomaly detection on EV logs using FHC. Alon, can you hear us?
Yes. I'm sharing my
Okay.
screen now. Can you all see my presentation?
Yes, we can hear you. We can see your presentation. But now it's in presenter mode. Can you switch to the different screen, because we can see the presenter mode here?
Wow, I don't know how to do that. Let me try to share my entire my application. Just a second. Okay, let me try to show my screen again. Can you see my presentation?
Yes, we can see it.
Yeah, I don't know how to do it. Let's just stick with this. Okay. So this is we'll describe another activity in ELECTRON, which was partly mentioned before. This is a privacy-preserving anomaly detection over encrypted private logs coming from electrical vehicle charging stations. This is in collaboration with the PPC. It's the very large Greek electrical company that has a network of these electrical vehicle charging stations. And we're using FHE, which I'll describe now, in order to do this analysis privately, while preserving the privacy of these logs. I'm from IBM, by the way. Okay, so let's see what this, reminder what this FHE is, fully homomorphic encryption. So on the left, you see an example of a user that has some private data, let's say 3 and 5, and the user encrypts this with the secret key. And the ciphertexts are now 9 and 1, so 9 encrypts 3 and 1 encrypts 5. If this is normal conventional encryption, and you just add up these encryptions, this 9 and 1, you just get garbage, right? You get 10, which happens to be the addition of the sum of 9 and 1. If you decrypt this garbage 10, you get the garbage out. So 42 is definitely not the sum of 3 and 5. Yeah, so this is so in conventional encryption, there's no reason to assume that if you add the sum, if you sum up the encryptions of numbers, you get the sum of the numbers. But this is exactly what happens in FHE, fully homomorphic encryption. So if you add up the encryptions of 3 and 5, you get an encryption of 8. This is the homomorphic aspect of this process. And the same goes for multiplication. So you can, if you multiply 2 encryptions, you get an encryption of the product. And if you can multiply and add, you can basically do any computation, because if, let's say you want to evaluate compute the sine function, you can just use a polynomial, Taylor polynomial for sine, and polynomials are just additions and multiplications. So in a sense, you can compute any function that you want under FHE. There are some caveats. It's a bit slow, and all these polynomials can make it even slower. So if you want to compute square roots or division, it's possible, but it's a bit harder, and there's also some noise involved. But in general, you can say that any computation is possible, and that's why it's called fully homomorphic encryption. You can basically compute any function. So if you can compute any function, you can also compute train any model that you like. You can train, ChatGPT-like transformer networks, which is just a computation. You can do it under FHE, and actually do that. And once you're able to compute to train models and inference models, you can have this very popular use case of FHE, where a user starts by sending encrypted private data to the cloud. The cloud trains some complex model using these FHE computations. the cloud cannot see, the cloud server cannot see the data because it's encrypted. It cannot see the model that it itself computed because, again, everything is done under FHE. And now once you have this encrypted model in the cloud, the user can go ahead and send new data, encrypted new data, and let the cloud compute the inference over this encrypted model. So then the cloud computes the inference. Let's say it's a yes or no. And this answer, this yes or no, is also encrypted and sent back to the user. And only the user has the secret key that is able to decrypt all these encrypted data. So this is the most popular use case scenario for FHE. The user is using the cloud for storage or for computation, and everything is private. The cloud does all these computations and storage services without being able to see anything, neither the input data nor the output results. Okay, so this is basically FHE. And we want to use FHE in ELECTRON together with PPC. This is the electrical company in Greece, which has these charging stations. We want to use FHE to analyze private logs coming out of these charging stations in order to detect a possible attack. So this is the attack that we're interested in. So you have a vehicle that comes along and wants to charge the battery of the electrical vehicle. And the risk is that all these while the charging takes place, the charging station sends over to an operator at the top here. It sends logs describing the state of the charging, and according to this state of the charging, the user is going to have to pay for the energy that he used. So this is normal behavior. But if the user, if the driver of the car happens to be an attacker, and is able to take, corrupt all these messages, there is a risk that the attacker will be able to reduce his payment because it reduces the messages that describe the amount of energy that was actually used. So if some of the messages describe the power that is actually consumed, and the attacker is able to corrupt these messages and lower the values, then the operator will think that less power was consumed, and the driver will pay less than he was actually supposed to pay. So this is a kind of energy theft scenario, and we are going to capture this event. And again, all these logs that have been sent, these OCPP protocol logs that have been sent around, are all private information because it describes a private car of a private owner. You're not supposed to send it anywhere you like, and yet we are able to send it encrypted under FHE to the cloud, and the cloud is going to compute and detect this kind of event under FHE while preserving the privacy of these logs. So this is exactly here. So what happens is, again, you start from the left. The charging station encrypts these logs that describe the charging state. These encrypted logs are sent over to the cloud. The cloud trains a model, a time series model, that describes the normal behavior of the normal patterns of the charging station for that particular vehicle or that particular charging station. And once you have this model that describes a typical normal time series, you are also able, the cloud is also able to, under FHE, under encryption, also predict what is the next, supposedly next value of the signal. And if this predicted next signal is very much different from the actual observed signal, then this is declared an anomaly and is possibly indicative of an attack of the type that we are interested in. And so all the computations here, the data that's been sent to the cloud, the model, the time series model, the next predicted next value, and also the declaration of the alert, all of this is done under encryption. So the cloud just makes these computations without seeing anything, just like a blind horse that can also only see the data it's handling, but not understanding anything semantically about what's going on. So again, the privacy is preserved, and yet the cloud is able to make all these computations and send an alert report, encrypted alert report, back to the key owner, the secret key owner. Any questions? Okay, we continue. So I mentioned the RIMA. RIMA is a popular time series model. Again, time series model tries to model the pattern of some signal or some value over time. The particular characteristic of RIMA is that it assumes that the value of the signal at some time depends linearly on the value of a previous on previous values of that signal. So and also on previous values of the errors of the prediction. So here you see an example of a formula where the value of the signal at time t depends linearly on the value of the signal at time t minus 1, that's the previous signal, and also on the error at the previous signal. And all these parameters, the mu and the phi1, the phi2, and the theta2, are all, this is what makes it a linear relationship. So we have to, these are the characteristics of the model. So when you train an ARIMA model, your job is to find these mu, phi1, and theta1. Okay, and that's exactly what happens. So in the training stage, we send all this, the time series itself encrypted to the cloud. The cloud trains this time series and comes up with all these parameters, the mu and the phi and so on. And this is done again under encryption in FHE. And actually, this was the tricky part. We were the first ones in the ELECTRON. We were the first to compute to model a time series model under FHE. And the difficulty is here when you compute in order to come up with these parameters. You basically have to solve a system of linear equations, and this was not done yet under FHE, and we were able to do it. Okay, so once you train the model, you have all these parameters, so you know the formula. And to predict, you just have to plug in the values inside the formula. You have the time series, so you can plug in zt minus 1 and the errors, and you can come up with the next predicted value, the final predicted value. So prediction is relatively simpler. And once you can predict, you can also compare the predicted value with the actual value and see if the difference is too large. If the difference is large, this is considered an anomaly. And again, the fact that it is large is also encrypted. So the server can compute the difference. The difference is encrypted, and even the decision if it's high or low, the difference is also done under encryption. So the cloud doesn't know if the anomaly actually occurred. It can just create an anomaly report and send this in encrypted form back to the user. Okay, so that was ARIMA. And this is the basic architecture of what we did for electrons. On the left, the process starts by PPC, that's the circle there, sending encrypted logs, event logs from the charging stations over to what we call the aggregation unit. We aggregate all the activities in the log for let's say a minute. So every minute we have a sum of all the charging activities in that minute, and we take all this aggregated data and we encrypt it. That's the orange part on the right there, and this encrypted log or encrypted aggregated log is sent to the cloud. That's the IBM part in the center. So IBM takes these encrypted logs, trains the ARIMA model, creates an encrypted ARIMA model there on the bottom, and is now able to take new logs coming in from the left and compare the predicted value to what is actually observed. And according to the difference, it can create an encrypted alert report that's on the right. And this is sent back to PPC, which has the key. And PPC is able to decrypt it and see the result, if there was actually an alert or not. One thing is not shown here is that we actually also collaborated with Thales, and that's another partner in ELECTRON, which added a quantum safe authentication signature over all these messages, because one aspect of FHE is that the key is public. FHE is a public key encryption scheme, so everybody has the encryption key, so anybody can basically change the messages. So in order to avoid that, we have a quantum safe signature provided by Thales, which was added on top of these messages. Okay. Finally, the results. So we actually, to test the system, together with PPC, we created a set of charging session log files, or 7 normal charging sessions that we can train with, and 3 charging sessions that were tempered. So they actually have the event that we were looking for, where the charging is the power consumption is lower than the actual power that was consumed. And we try to detect this anomaly under FHE. So at the top, you see the normal logs, and on the bottom, you see the abnormal log. On the left, what's called the WH curve, that's the power consumption. So you see the power consumption obviously goes up as the charging session continues. On the right, you have this SOC curve, that's the state of charge of the battery. So naturally, if the higher the power that was consumed, the higher the battery is charged. So both of them go, there is a correlation between these two graphs. And the correlation you see on the right, that's the WH divided by SOC curve. So naturally, this is more or less constant. So the SOC grows constantly, linearly together with the amount of power consumed. And this is normal behavior. In the unnormal behavior, on the bottom, you see that as time goes by, the power consumption grows, but the state of the charge of the battery grows, but the power consumption is very low. It looks as if very small power was consumed, and yet the battery is fully charged. So this is exactly the kind of attack that we're looking for. And obviously, this curve on the right, bottom right, is anomalous. So we were able to capture these kinds of anomalies. There was one interesting case where one case which was supposed to be normal, we actually reported it as abnormal, but it turned out that it was indeed the same charging station, but a different car. So somebody was using a different car at inference time than was actually used at training time. So obviously that was also considered an anomaly, because the charging patterns also depends on the type of vehicle, and so it was declared as an anomaly, which is okay, because what happens in this case is that, let's say, they use the PPC, the security control person at PPC will see that there was an anomaly, will check and see that actually it was a different car, which explains an anomaly. So it's easy to deduce that it's not really an attack. That's it. Thank you.
Thanks, Alan, for your presentation. I don't know if you have any questions here or from the audience in the Teams.
Hello, Alan. Just speaking from
Yes,
Atos.
yeah.
Can you hear me?
Yes, yes.
Okay. What about training on watch data? Is it affected your model on this or not?
The more data we have, the more accurate the model is going to be, obviously. So
yes, but the FHE, the full homomorphic encryption, does it affect the training of watch data, or it's slower, it's faster when you have watch data?
Yeah. So like I said, we are working in time units of 1 minute. So actually 10 minutes. Every 10 minutes we aggregate the logs and we pass them on for analysis. So obviously, if there's much more activity in these 10 minutes, it won't affect aggregation, because aggregation will stay the same. So that should be okay. And the aggregation is done in plain text, so we don't really care about the
yes, correct. This is the part we don't care. What we care is about how you scale on the cloud when you have, instead of 1 gig of data, 500 gig of data to train on, for instance.
Right. So yeah. So you're right that FHE is much slower than plain text computations. So definitely, if you have, let's say, let's assume that we have suddenly 1,000 cars, more than we usually have. So you have to do 1,000 times more computations under FHE than we usually do. Everything is scalable. If you have 1,000 more data that you want to analyze, you have you can buy 1,000 more computers than you usually have. It just depends on the amount of investment that you want to put into this. But I can just add that FHE is becoming more faster and faster and very practicable. We're using it for large data. Like I said, we're actually doing ChatGPT-like training for transformer networks, which is very large networks with billions of weights and very large data sets. It's not in real time, as in this case. This case is a real time scenario. So ChatGPT training is not real time, but
Yes.
just indicative that the performance of the FHE is definitely increasing, and you are able to handle much more data than you used to. But having said that, obviously, if you have more data that you want to consume to analyze, you need more computing power. So yeah.
Okay. Very well. Very well. Very interesting with the ChatGPT. It's a very interesting direction and privacy preserving training.
Yeah.
Okay, very well. Thank you, Alan.
Thank you. Bye.
I don't know if you have any more questions. Otherwise, we can proceed with the next presentation. It's about the proactive reconfiguration, energy balancing, and grid restoration. And Antonis Vulgaridis from Center for Research and Technology, ELAS, will do the presentation.
Yeah, the control.
Okay.
Hello everyone. This is Antonis Vulgaridis from CERT. Today I'm going to present to you one of the collaborative scenarios that we worked on during ELECTRON, which is mainly focused on the components described previously by Panagiotis under the bridge framework. This scenario is about proactive reconfiguration, energy balancing, and grid restoration. And the participants were also UCY and Isotrol. So the outline of the presentation is first, I'm going to introduce a little bit the scenario and the objectives of the scenario. Then I'm going to talk a little bit on how this is positioned inside the ELECTRON architecture. And then we're going to go through the scenario flow a little bit and how the scenario is working. And then I'm going to, let's say, play a short demo where you can actually see how the scenario is visualized. For this scenario, we are working under the assumption that a critical large-scale attack is in place in the grid, and a proactive reconfiguration procedure is considered as, let's say, a remediation action. Throughout the whole process, we are working towards energy balancing, and then after the attack is cleared out, we move to the grid restoration phase when we, let's say, restore the grid to its normal operation. The components involved, as you can see, is ISODIN with the grid reconfiguration, ELIS with the optimal hierarchical control, and BIM with the blockchain inter and intra microgrid transactions, and of course the UCY sandboxing environment where we all visualize the grid as it is. So some words related to the sequence diagram and how, let's say, everything is working under normal operation. First, from the sandboxing environment, which is, let's say, being considered as the test bed that we apply our components on. We write the measurements through a ThinkSpeak interface, and from there, ELIS reads the grid configuration and measurements and calculates the optimal set points that are being sent back to the sandboxing environment. Then, let's say, the same procedure is going on by sandboxing, reading the updated set points from ELIS and writing back those through ThinkSpeak. and ELECTRON performs the same, let's say, optimal the optimal set points and send them back to the big component for the, let's say, energy transactions. Then the second phase is the abnormal operation, where we actually have, let's say, a cyber attack, and we identify a cyber attack at bus 5 under this current example. Isodine, let's say, reads the grid forming and provide a new grid configuration. So in a sense, let's say, suggest some changes in the grid configuration in order, let's say, to minimize the effect of the cyber attack on the microgrid. And from, let's say, this configuration, the DSO accept or decline what, let's say, suggestions were coming from Isodine and performs the necessary changes. Then, again, ELECTRON reads these configurations and provides the optimal set points during abnormal grid operation. Then the final phase is the restoration process, where we actually, let's say, work under the assumption that this attack is cleared, and there is a message from Isodine to ThinkSpeak that everything is okay, and now you can restore back the grid to, let's say, to its normal operation. So Isodine provides some new suggestions on, let's say, status breaker changes, and the DSO accepts or declines them, and so on and so forth. Then ELECTRON recalculates the optimal set points during, let's say, grid restoration phase, and then provides the unit commitment schedule to BEAM in order for this blockchain energy-related component to perform the energy transactions and write them back to the blockchain network. So again, as I told before, the video that you're gonna see in a couple of minutes has 3 main phases. The first, again, is the normal operation, where more or less I already explained that this involves the sandboxing environment, which is used as a GUI, and we can see actually the status of the breakers there under normal operation. ELECTRON performs its, let's say, optimal scheduling and send them back to sandboxing, and this is being visualized through the sandbox GUI. While during the cyber attack, and when the cyber attack is occurred and identified by the system in power substation number 5, but again, this scenario can also be applied when there are multiple attacks being, let's say, happening on the grid. But for this example, we only showcase, let's say, a cyber attack on one power substation. Then under this, let's say, this phase, under the attack phase, Isodine sends a warning to the sandboxing environment and runs exhaustive search for optimal reconfiguration of the grid, then provides some suggestions and some advice to the DSO for optimal reconfiguration and, let's say, to being used as mitigation actions. The DSO accepts, again, or declines based on also, let's say, based on its own decision, these suggestions and performs the reconfiguration of the grid via the GUI of the sandboxing environment. ELECTRON recalculates the optimal set points, and this is the, let's say, the process under the attack phase. The final, again, phase is the grid restoration phase, where Isodine informs that the attack is cleared, provides, let's say, the suggestions for restoring the grid to its normal operation. The DSO, again, performs the new optimal set points to the sandbox environment, but also to the BEAM component. And then BEAM starts the energy markets, performing some energy transactions and writing these transactions to the blockchain network. This is more or less the workflow of the video. I can try to play the video from here, or I mean, I don't know if it's...
Try to change the settings. Maybe we have some problems with the mic, so I will try to do it from here.
Okay, please, others.
So,
may I stop sharing the screen and...
take over.
Okay.
Let's see.
So as you can all see in this, let's say, slide
normal
here,
operation, the DSO monitors the operation and power flow exchange between the main power grid and the 3 grid-connected nanogrids through the use of the graphical user interface of the sandboxing environment. Then, ELIS calculates the optimal power exchange between the main grid and each of the nanogrids and send the optimal set points for controlling the battery storage systems, charge or discharge state to the sandboxing environment. We then move to the attack phase, where we assume that a critical cyber attack was detected within the network station, serving the power substation number 5. To avoid any propagation of the cyber attack, Isotin component sends to the DSO, in this case the sandboxing environment, a warning message and viability suggestions for optimal configuration of the grid in order to minimize as much as possible the amount of load not served. Then, the DSO accepts the suggestions coming from the Isotin component and performs the reconfiguration of the grid by changing the status of the circuit breakers as indicated by the change of colors in the graphical user interface of the sandboxing environment. While monitoring the microgrid, ELIS detects the change in the circuit breaker status that results into a topology reconfiguration and calculates the new set points for the battery storage systems and send them back to the sandboxing environment through the ThinkSpeak communication channels. When the attack is cleared, Isotin component sends viability suggestion for restoring the grid reconfiguration to its normal operation conditions. Following these suggestions, the DSO performs the needed breaker status updates, as again indicated by the change of colors in the graphical user interface of the sandboxing environment. As previously, during the microgrid monitoring, ELIS detects another change in the breaker status that results into another topology reconfiguration by reading the updated status of the breakers from the ThinkSpeak communication channels, and once again calculates the optimal set points for the battery storage system units. The updated set points are then sent back to the sandboxing environment and visualized through the graphical user interface. Finally, the last step of the whole procedure is that we enter the energy transaction stage, where ELIS sends the unit commitment schedule to the BIM component, and in its turn, BIM starts the inter and intra microgrid energy markets and performs the energy transactions. Thank you very much for your attention.
Right, so that was it. This was the, let's say, the demonstration that I was talking about, and this concludes the presentation for this collaborative scenario. I don't know if you have any questions.
Thanks for your presentation.
Thank you.
So we proceed with the next presentation. It's let me check that. It's about the print framework. So just a minute to find the presentation. So we have Konstantinos Vougaridis from Demokrition University of Thrace. So Let me share the screen.
Hello everyone, my name is Konstantinos Vulgaridis. I am part of the DUTH team that worked on the Prince portal in collaboration with Technalia as part of the ELECTRON project. This is going to be a short demonstration on the architecture, impact, and evaluation of the Prince portal. And by the end of this presentation, we are going to show a demonstration video on the functionality of the portal. To begin with, the Prince portal is the result of work package 6 of the ELECTRON project titled AR, VR, Aided Cybersecurity Training and Certification in Energy, Power, and Energy System Infrastructures. It consisted 4 main tasks, with the first one being the main one on the methodology that was followed to construct the Prince portal, including valuable input that we acquired by our energy stakeholders. The remaining 3 tasks were related to the creation of all the training material and software that was implemented in the courses of the Prince portal, the AR and VR educated tools that were utilized for an enhanced learning experience, and last but not least, a certification system in order to certify the acquired skills of EPES employees. The results of these 3 tasks are also unified and implemented within the full scope of the portal, and are also going to be presented as part of our demonstration. The Prince portal is directly related to the objective 5 of the ELECTRON project, about the realization that many cybersecurity risks begin within EPES infrastructures, as well as the realization that there is a need for the creation of a cybersecurity training platform that utilizes AR and VR educational tools for EPES employees, and to certify the newly acquired skills in order to prevent future cybersecurity issues within such infrastructures. Our objectives through the demonstration is to showcase the methodology that was followed in order to correlate cybersecurity issues, solutions, as well as the roles that take place during such events, to present the full scope of the Prince portal, to demonstrate the didactic content that was implemented within the courses, as well as the AR and VR educational tools, namely AR Tutor, Process AR, and Kairos, to demonstrate the capabilities of the CyberRange facility and the ELECTRON avatar component for the completion of virtual exercises, and last but not least, the certification system that was implemented by the end of each course. Here you can see the main architecture of the Prince framework. It consisted of 3 phases. The first one is related to the design, about the collection of all official guidelines and educational resources in order to construct all of the training curriculum and courses that were implemented, as well as to design the virtual exercises in order to help trainees, and specifically the EPES employees, to develop practical skills. The next phase is the delivery phase. It's about the development of the Prince portal that combines the training material with the AR and VR educational tools in order to provide an enhanced learning experience. Also, the Prince portal is directly connected to the CyberRange facility for the completion of the virtual exercises, and the ELECTRON avatar component that provides additional tips and hints during the completion of such virtual exercises in order to help the trainees to complete them. And the last phase is the assessment phase, which basically asks the trainee to complete a theoretical and practical assessment to verify the skills that were acquired during the courses and to receive the respective certificate. The results of the deliver and assessment phase are also part of the demonstration that you will see at the end of the presentation through our video. Regarding the impact of the Prince portal, ENISA identifies that many cybersecurity issues begin within the EPES infrastructures and specifically from its employees, either due to lack of cybersecurity awareness or user errors. This is where the Prince portal attempts to resolve such issues, through the creation of an effective cybersecurity training platform in order to reduce the unintentional damage as much as possible through the utilization of AR and VR educational tools in order to increase engagement and provide a better understanding of complex concepts of cybersecurity. Also, this demonstration contributes to all the KPIs related to Prince that are also provided in deliverable 2.3 of the ELECTRON project. Regarding the evaluation, part of the evaluation process was completed through the use case 1, scenario 1 of work package 9, titled Phishing and Spear Phishing EPES Training and Certification. A total of 13 participants, 13 employees of our partner JSC participated in the evaluation process, and they were separated based on their roles in the different courses. Specifically, we had 3 EPES trainees, 5 SCADA administrators, 2 SCADA MSP operators, and 3 security administrators. Upon completion of the courses, a questionnaire was shared among the participants in order to collect feedback on their interaction with the Prince portal, the utilization with the AR and VR educational tools, as well as the general perception of the technologies that are implemented within the platform. Here you can see a chart about the general experience of the participants. It is based on 5 different questions on the successful completion of phishing training, and cyber attack detection training, as well as the accessibility to the platform and the utilization of the VR, AR educational tools and the cyber range facility. As you can see, the majority of the participants strongly agreed that the Prince portal is effective and successfully fulfilled its intended purpose. All the details about the questionnaire and the results are available and will be provided in the related deliverable. And here you can see the steps that we will present through our demonstration video, which is basically about the access to the Prince portal, the didactic content, the utilization of the AR tutor, process AR, and KROX tools as part of the learning process, the functionality of the ELECTRON avatar component and the cyber range facility for the completion of the virtual exercises, and last but not least, the certification process about the theoretical and practical assessment, and the steps that the trainee needs to take in order to receive the certificate, an issued certificate, which in our case was Technalia. Now we could play the video. Yeah.
Welcome to the demonstration video of the Prince framework. Prince is the training and certification framework on cybersecurity awareness, developed in the context of Work Package 6 of the ELECTRON project. To begin the demonstration of our scenario, let's access the URL link of the Prince portal. Initially, an Energy Power and Energy System employee registers for an account in the portal by providing some essential information. Then, with the registered credentials, the user logs into the platform and depending on their role, for example Security Administrator, they enroll in the respective course. Following the example of the Cybersecurity Awareness for Security Administrators course, the trainee is called to complete 4 topics corresponding to threats on phishing, denial of service, spoofing, and unauthorized activities, with interactive theoretical and practical material. Then, the trainee can proceed by practicing their gained knowledge through the section of cyber exercises and complete the course with the respective certification exam. At the beginning of the course, the trainees can find some introductory information on the course's scope, as well as a study guide, instructions on how to use the AR tutor, KROX, and process AR tools, an announcements discussions board, and a chat room for real-time conversations. Let's go through the phishing course. as the first indicative example for the functionality of the Prince portal. Through the specific course, trainees will learn how to detect, prevent, and respond to different types of phishing attacks. First step of the training experience is a thorough presentation, enhanced with narration features and powered by the AR Tutor tool. Starting with the phishing presentation, the trainee can utilize the AR Tutor mobile application to scan the presentation's QR code, download different types of augmentations that will support their learning experience, and display them by pointing their camera to the signified positions of the slides. Throughout the presentation, there are available URL link augmentations redirecting the trainee to pop quizzes within the application's environment in order to test their understanding of the theoretical knowledge acquired on the previous slides. The trainee can fully interact with all of the presentation's augmentations through simple finger gestures. Specifically, pinching to zoom in or zoom out, tapping to play or pause videos and audio files, and sliding for rotations.
Ensuring a safer digital environment.
Sandboxing is a security technique that isolates programs or processes from each other and the underlying system.
Once an activity is completed, it will be enabled to be marked as done as part of the trainee's progress within the course. Upon completion of the presentation, the trainee can access additional material on related lecture notes, suggested further reading, and a self-assessment questionnaire on phishing. Next step in the trainee's learning experience is the utilization of the Process AR tool. For the respective example, we will move to the Denial of Service module, where trainees will acquire knowledge on different types of DOS attacks, their concepts and anatomy, as well as protective measures. Through the respective exercises, the users are asked to identify data from servers in augmented reality panels. First, they have to calibrate the environment to interact with QR codes, and to load the panels, they should click on the QR button and focus the camera on them. The particular example prints logs from the console and depicts a list of active connections interacting with the server. Specifically, the objective is to identify which machine receives a DOS attack. Each machine must have its own QR code linked. As we can see, the second machine shows symptoms of having a SYN flood DOS attack. AR panels can show quick information and use it simultaneously. Let's move on to a VR-based exercise on the Kerox tool. For the specific exercise, the trainee wears a VR headset in order to interact with the virtual environment. By wearing the helmet and holding the controllers, the trainee can look around and interact with the icons that are presented in front of them. The respective icons provide valuable information that will assist trainees in solving the provided question. If the answer is correct, a new stage begins that may take place in a different location of the virtual environment. Overall, the main purpose of the Kerox tool is to place users in a training environment that simulates real-life situations with gamified principles that will further enhance their learning experience. If the trainee fails to answer the question correctly, a notification sound is played to signal them to proceed for another attempt. Once the trainee completes the different learning modules, they can proceed to the cybersecurity exercises section to practice their acquired knowledge. When the trainee enters an exercise, an avatar is displayed on their screen, explaining the upcoming challenge that they need to resolve. Also, the avatar is integrated with AR capabilities, making it possible for the trainee to display it through their mobile device.
Identify this information flow and determine which APN MAC pair corresponds to the scanner.
Then the trainee can proceed to the Cyber Range platform for the resolution of exercises while utilizing two different tools. The first one is the Root the Box tool, which requires the trainee's registration and logging in. This tool contains a set of exercises called missions, with each mission having a thorough description of its context and objectives, and a set of questions called flags, with included hints on questions of high difficulty. To answer a flag, the trainee registers their answer through the Submit button with a system notification of whether they answered correctly or not. To answer a question correctly, the trainee must access a second tool, the dashboard, which receives real-time network traffic from the Technalia substation, presented in a graphical and organized manner, and allows the trainee to filter the data in order to answer the questions. In addition, trainees can monitor the progress of other participants through the respective scoreboard. When trainees complete all of the course activities, they can proceed by taking the certification test and the practical assessment through the Cyber Range platform. Starting with the certification test, a summary page is presented to the trainee, showing their progress on any potential attempts on taking the exam. Specifically, the certification exam consists of a collection of multiple choice questions based on the knowledge acquired throughout the course's modules and requires a minimum of 70% as a passing grade. After successful passing of the exam, the trainee can proceed by completing the practical assessment. In a similar manner to the Cyber Range exercises completed for the previous modules of the course, the trainee is asked to complete a mission while utilizing once again the root the box and dashboard components. After careful checking of the instructions, the trainee accesses the dashboard component to filter the required traffic data and figure out the correct answer for the exercise, and then returns to the root the box component to submit the answer to the respective flag. Considering the passing of the exam and the successful completion of the practical assessment, an unsigned certificate in PDF format is issued to the trainee, which can be then submitted for an official signature by the certification authority, that is in our case Technalia. Thank you very much for your attention to the demonstration of the Prince framework.
This was our demonstration. If there are any questions, I would be happy to answer. Okay, thank you very much.
So we move to the final presentation. It's about the ELECTRON Lighthouse. So just a minute to find. So Jesus will say a few words, and then we will have a video for you.
Oh, hello to everyone. Good afternoon. I'm Jesus Rosario from Alter Technology, part of the ELECTRON project as to Spain. I'm going to show you a small demo of the ELECTRON Cybersecurity Lighthouse web portal.
For the dissemination event in Hamar of the ELECTRON Cybersecurity Lighthouse. This portal will be a source of information towards users who want to have more knowledge about legislation, regulations, EU institutions, and the main acts, directives, and standards for ensuring cybersecurity in the European energy sector. The website contains a section dedicated to the ELECTRON project with information, the objectives, and the link of the website of the project. As mentioned, above, the web portal is subdivided into 3 main sections containing sources of information that we consider to be very useful for users. The first is the current European energy policy, which contains the main organizations related to cybersecurity. For example, in the ENISA section you can see its relationship with the energy sector and with different directives such as CSA and NIS. For more information, there is a link to their official website at the bottom. If we click on the main sections, we will see that it will show us all the subsections it contains with a short summary of each one. The next section is the European Union Acts and Directives, where you can find the Cybersecurity Act, NIS2 Directive and CRA and more. The same for the red directive, which shows information on the 3 new cybersecurity parts that have been recently incorporated with their requirements, mechanisms, and the different types of assessments implied, and their links below. The last main section is the main standards section, which contains the main standards to ensure a safe environment in the energy sector, such as IEC 62443, ISO 27001, or ISO 21434, among others. The portal contains a section of the most frequent asked questions that the users may have while reading the content of the web portal. Here they will be able to resolve some of those doubts or questions they might have. The contact section has been made to improve communication with users. Through this channel, users will be able to get in touch with our team to resolve any questions or concerns related to the topics covered on any part of the website. Also, a new feature is the search icon. Clicking on this icon will display a text box in which users can enter keywords or phrases related to the content they wish to locate. Once the search is performed, the system will process the request and present a list of relevant results. Each of the results displayed will include a short summary, providing a brief description of the corresponding content. This functionality is designed not only to improve the accessibility of the content, but also to provide a quick and useful overview of the content. The forum space aims to enhance a constructive dialogue on cybersecurity challenges, threats, and best practices, as well as to promote cooperation and common understanding among EU member states. To use the forum, users must register. To do so, the page will take you to a registration and login window. Their users must enter their desired username to appear on the forum and their email for verification, and set a secure password. After clicking on Register, a confirmation email will be sent to you. There will be a link where user must set a secure password. Once the user has successfully registered and logged in, they will be able to use the forum. In the forum, the user will be able to actively participate in the various subforums that have been created. They will be able to create topics and be able to answer questions and opinions of other users.
Okay, that's all.
I don't know if you have any comments or questions. Okay.
Yeah, it's open. The only thing is the forum that you have to register to use it.
How has been your experience with the forum?
It's developing. We are going to deliver the final version at the end of September, more or less. So it's beginning only.
Okay, any more questions? Okay, just a minute. Presentation, so I would like to Thank you all for your participation. I will share with you in the chat a link with a short questionnaire regarding your experience from today's event. I would be happy if you spare 5 minutes of your time and respond to that.